The first flow control algorithm that we'll study of is called stop and wait ARQ. You can think of it as an algorithm or as a protocol. Both of them mean the same thing. A protocol tells you a set of rules that we have to follow. So does an algorithm, actually, if you think about it. Here, ARQ basically means automatic repeat request. So automatic repeat request, right? Automatic repeat request. So unlike the typical expansions that we use here, A is taken from here, R is taken from here, and Q is taken from here. It's not written as ARR. It's actually written as ARQ. Now, we often, to understand any flow control algorithm, the easiest way to understand is through diagrams like this. So let me explain this diagram so that you understand this. Okay. So you have your sender here, you have your receiver, and there is a medium between both of them. Right? There is some either a twisted cable or a coaxial cable or a fiber optic cable or a wireless medium, right? So you have a sender and a receiver, and remember that this is time axis as mentioned here. This is also time axis. Now let's understand the sequence of steps that occur. Okay. So I have a binary variable. Remember, I have a binary variable here called S, and on the sender side, I have a binary variable on the receiver side called R. Okay. First, let me explain how it works in the simplest case. Then I'll explain you the complicated cases. First, the sender at this time, the sender sends frame 0 to the receiver. Okay, while it is sending it, the receiver does nothing. Okay, the sender sends frame 0. Now, after the receiver receives frame 0, it spends some time called as the processing delay. So this small amount of time, right, is called processing delay. My minuscule amount of time actually. And during this time, look at this. The sender sent frame 0. The frame 0 successfully reached the receiver. Now, what the receiver tells now is, okay, what the receiver has to send an acknowledgement back saying, yes, I have received frame 0. Now send me frame 1. Okay, that's what this acknowledgement 1 basically means. This ACK1 basically means I have received frame 0. Now send me frame 1. Now this acknowledgement also has to travel through the whole medium. Remember, this frame 0 traveled through the whole medium, reached R, then R took a small amount of processing delay, which is very small, right? During this processing delay, R actually created this acknowledgement packet, right? And it sent the acknowledgement here. Now, once the sender receives the acknowledgement packet from the receiver, then the sender changes this binary variable to 1. Okay, and now it sends frame 1. Look at this. The sender was waiting for acknowledgement 1. The sender was actually waiting for acknowledgement 1. As soon as because it sent packet 0, after packet 0, it has to send packet 1. The way it will send it is, it will send frame 0, frame 1, frame 0, frame 1, frame 0, frame 1, so on and so forth. Right? That's the order in which it will send. It will send. Okay, frame 0, then I got acknowledgement 1. That means the receiver received frame 0. It is asking me to send frame 1 now. So I change my binary variable to 1, and then I send frame 1. After I send frame 1, I'll be waiting for ACK 0. So the receiver receives it successfully. Then the receiver sends acknowledgement 0. So this ACK 0 basically means, again, remember, okay, this is very important, right? After the receiver sends acknowledgement 1, it changes the receiver changes the binary variable to 1. Because now, since he has already sent an acknowledgement for 1, or since he has sent ACK1, which means he's communicating to sender that he has received frame 0 successfully, no errors in frame 0, successfully received it, and then he says, I want frame 1. Now he has to wait for frame 1, right? He has to wait for frame 1. So hence he changes his binary variable to 1, right? Now what happens? Now look at this. Now the sender sends frame 1. He's expecting frame 1. Perfect. He gets frame 1. He checks if there are any errors here. Again, we'll see how he checks errors later in this chapter. Okay, the receiver now checks if there are any errors during the processing delay. If there are no errors, he says ACK 0. He says, I got frame 1. Now I would like to get frame 0. So they alternate between these numbers 0, 1, 0, 1, 0, 1. Again, this frame 0 and the next frame 0 will contain different data. The numbering here, again, the binary numbering with only zeros and ones is the simplest scheme. right? We could have used non-binary variables here and actually had numbers for each, like 0, 1, 2, 3, 4 also. But this is the simplest scheme in which we can apply stop and wait ARQ. Look at how it's working. This is called stop and wait ARQ because look at this, I'm sending the data. I'm waiting for the acknowledgement from the receiver. Only when I receive the acknowledgement will I send the next frame. Only when I receive the acknowledgement from the receiver, then I send the next frame, right? So I send, I stop, I wait till the time I get acknowledgement, and then I stop again, I wait till the time I get acknowledgement, then I'll send. Okay, so that's why it's a very, very simple scheme. Now let's look at how much time it will take. Let's assume, so from the time I send, from the time the sender starts sending this frame, how much time does it take? Look at this. I have frame 0, right? Let's assume frame 0. Let's assume frame 0 has L bits, right? We have seen in the previous video about propagation delays and transmission delays, right? And let's assume the medium has a bandwidth B. So let's assume the bandwidth is B. Let's assume the bandwidth is B. How much time does it take for us to first place the frame 0 on the medium? It takes us transmission time. Look at this. What is the total time? For L bits, look at this. For L bits or one frame, how much time does it take for us? Okay, it takes TT, the transmission time, to place the whole frame, the L bits onto the wire or onto the medium. Then it takes TP to propagate it. Then it will take some time. It will reach, everything will reach the receiver. Then the receiver has some processing delay. Okay, let's call it T processing. Okay, this is propagation, this is processing. Okay, some processing delay. Then it starts sending the acknowledgement packet. Now it will take me some time to place this acknowledgement packet or acknowledgement frame on the wire. So let's call it as transmission time for acknowledgement packet. Then there will be some propagation time for the acknowledgement packet also, which will be equal to TP. Because propagation time is a property of the medium that you are using. So for this, see, propagation time for this will be the same. The transmission time for the frame will be different from transmission time for the acknowledgement, because the acknowledgement packet is actually very, very small. When I'm sending the acknowledgement packet, all I have to say is I have to place the receiver's address, the MAC address, the sender's MAC address, and I just have to place this number 1. So acknowledgement packets are actually very, very small compared to your data frames. Remember, your frames actually contain data that you have gotten from the from the layers above, right? Remember, we are in the data link layer, right? We are in the data link layer. Let's not forget that. Okay. So your frame contains actual data that you got from the layers above, right? So your transmission time for the frame is significant. So in this equation, if you notice, this processing time can be ignored to be very, very small. Okay, you can ignore this processing time. Okay, because what it does in the processing time is it simply checks the checksum. Again, we'll discuss how error checking is done. It's a very simple checking which can be done in hardware itself. So it's extremely fast. So we can ignore this for all practical purposes. We can also ignore this. For practical purposes, because the size of this, because it doesn't contain any data. This acknowledgement just contains the acknowledgement number, the source address, and the receiver's address, right? That's all it contains. So we can ignore these two and we can write, but you can't ignore the propagation time, because propagation time is a property of the medium. So which means for L bits, we are going to take TT, which is a transmission time from the frame, plus 2 times TP. Okay, let's start writing that. Okay, I'll just erase this and write it here so that we can work out the math here. Okay, so for L bits, okay, let me write this down. For L bits, it takes us TT plus 2 TP seconds, or 1 frame. L bits or 1 frame, right? Effectively. Now, amongst this whole time, there is a term called efficiency, which is often represented by this Greek symbol. Okay, so this is called as efficiency. Now, how do we measure efficiency here? Efficiency is measured as in layman's term, it is the useful time by it is the useful time. It is often by total time, right? Again, what does useful time here mean? That's a good question. So in simple terms, the time we took to actually transmit this frame onto this wire. Okay, so this is nothing but transmission time of the data frame by the total time. What is my total time now? TT plus 2TP. Okay, so look at this. Useful time here basically means the time it took the source to place the whole frame on the wire by the total time. Again, this is what is called as efficiency, right? Very simple here, right? Now I can simplify this. Let me erase this also and simplify it further. Simple mathematical simplification like the ones that we learned in our high school, right? So again, very often we have a term called as A. Okay, we often use this variable A to represent TP by TT. We often use this variable A to represent TP by TT, right? Now, if I want to represent this in terms of A, what can I do? Imagine if I divide both numerator and denominator by TT. So I can write this as 1 by 1 plus 2TP by TT. I'm simply dividing the numerator and the denominator by TT. Simple high school math, right? So this is equal to 1 by 1 plus 2 into A. So you can compute your efficiency. You can compute the efficiency of this whole scheme, of your whole algorithm. Okay, you can compute the efficiency of your stop and wait ARQ given a medium which has a specific propagation delay and given the transmission time for a frame or a packet that you have. Again, we typically tend to use the terms frame and packet interchangeably, right? This is how you can simply compute the efficiency of the medium, right? Very simple. Now, there is another mathematical term. Again, stop and wait ARQ is a very simple thing. There is another term called as throughput, also called as bandwidth utilization or effective bandwidth. Okay, again, I'm just introducing terms to you. This is just terminology, right? Just like efficiency, just like the way I introduced this term called efficiency and this term called A, which is often represented as TP by TT. Let me introduce a new term called throughput, which is also referred to as bandwidth utilization or effective bandwidth, right? So this is often represented as L by this total time. Look at this. So how much, see, look at this. I'm able to transfer L bits. Look at this. I'm able to transfer L bits in how much time? L bits in this much time, L bits in this much time, right? That's what I'm doing. So L bits in TT plus 2TP seconds, which means in 1 second, how many bits can I transfer? It is nothing but L by TT plus 2TP. So the throughput is always measured in bits per second. Throughput is always measured in bits per second in computer networks. Again, you might have studied throughput in computer organization or in operating system. That throughput is different from this throughput. This is throughput in computer networks, right? The throughput in computer networks is measured in bits per second, right? So in 1 second, I can transfer these many bits. Effectively, this much I can transfer. This is what I can effectively transfer. Now, if we simplify this, let's go ahead and simplify this. Okay. If we simplify this, we can actually arrive at this equation also. Again, what is B here? Remember, B is the bandwidth. B is the bandwidth of the medium. B is the bandwidth of the medium. If you recall, we have used this term B earlier, right? Look at this. B is the bandwidth of the medium, and we have said transmission time or transmission delay is L by B. If you're able to transfer a frame or a packet of L bits, if you're transferring a frame or packet of L bits, and if the bandwidth of the medium is capital B, right? So, okay, so now let's continue this. So what if I divide both numerator and denominator by B? Look at this. Or let's just do this. L by B into B. I can do this in the numerator. In the numerator, I can do this, right? Division by B and multiplication by B. Then I have TT plus 2TP. Okay. Now what is L by B? What is L by B? L by B, if you look at the previous, L by B is nothing but your transmission delay. So I can write this again now as transmission delay times B by transmission time plus 2TP. Now, what is this term now? Look at this. What is this term now? What is this term now? What is this term? This term is nothing but your efficiency. We defined efficiency as transmission delay or transmission time by the total time. That's how we have defined efficiency here, right? Again, this is only for stop and wait ARQ. Okay, because this is the total time it takes for your stop and wait ARQ. For other algorithms or for other protocols, it could be different, right? So now, if I have this, I can write this as efficiency multiplied by B, and that's what I've written here. Very simple, right? Again, here the terms are very important. Efficiency is defined as the time, the useful time, which is interpreted as the transmission delay by the total time it takes to send one frame or one packet, right? Now, similarly, throughput, which is measured in bits per second, is measured as is basically a throughput or effective bandwidth or bandwidth utilization. Basically says what is the total time it has taken for us, and in this total time, how many bits have we sent? Using this, I can measure what is the effective number of bits per second I'm able to send using stop and wait ARQ. Again, here we are assuming that everything is going perfectly well. In the real world, things will go crazy. For example, your frame 0 may have gotten corrupted by some noise. In electronics, right? In electronics, the hundreds of things can go wrong and create noise or disturbance, or it could corrupt the data, right? So this is see, all the math that we are computing here is assuming that everything is working perfectly, because the total time that we are taking here is for the perfect scenario where I'm sending a frame, I'm getting an acknowledgement, I'm sending a frame, I'm getting an acknowledgement. There is no loss or corruption of data anywhere. Okay, that's an ideal scenario. So in an ideal scenario, if I have a medium with bandwidth B, and if my algorithm's efficiency is eta, then I can say my throughput or effective bandwidth is eta multiplied by B, bits per second. That's what it is. Okay, very, very, very simple. Again, you don't have to remember any of these formulae. You can derive them on the flow, because we've seen how to derive them, right? High school level mathematics. That's all there is here, right? So now let's take special cases now with stop and wait ARQ. What happens if a frame is lost or corrupted? Suppose there is a frame. Okay, let's take the example, right? Let's understand it with the diagram. Again, these diagrams are the best way to understand it. So your sender sends frame 0, cool. Your receiver is expecting frame 0. Look at this. Your receiver is expecting frame 0. We got frame 0. Frame 0 was perfect. No errors, nothing. It sent acknowledgement. After it sent acknowledgement, it will start waiting for frame 1 now. So look at this. After it sent acknowledgement, it is changing its R value to 1, because now it's expecting frame 1. As soon as it got acknowledgement, it says, let's start now sending frame 1. So it sends frame 1. But frame 1 is lost somewhere in the medium. Remember, there is a medium here, right? There is a medium. Either it is lost in the medium or it got corrupted. Something like that happened, right? But till the time the receiver does not receive frame 1, it will not send an acknowledgement. Look at this. Look at the catch here. It sent, see, this sender, because S equals to 1, because it got ACK1, right? Because it got this packet ACK1, it is sending frame 1. But frame 1 got lost somewhere. Either it got corrupted or it didn't receive receiver itself. We have to account for all of them. When we are designing a protocol, we have to design for all forms of eventualities. We have to take care of all boundary cases. Okay. So let's assume frame 1 got lost, and we typically draw it in these diagrams like this, saying lost. Now, till the time frame 1 does not reach the receiver, receiver will not send an acknowledgement. Now, till the time the acknowledgement is not sent, the sender can't send the next frame. So what happens now? So to handle situations like this, there is something called a timeout. So the sender, the moment it sends this frame 1, it starts a timer. It starts a timer on its side. Okay, it starts a software timer or a hardware timer on its side, right? And it says, okay, let's assume this timer is, let's say, 5 seconds. Let's just say the timer is set to 5 seconds, which means it will wait for 5 seconds to get a acknowledgement. It did not, if it does not, see, look at this. This timer is waiting for 5 seconds here. this whole time period from here to here, this whole time period from here to here is 5 seconds. Because this is time axis, right? Let's not forget that. This is your time axis. So it waits for 5 seconds. It did not get it. Then it realizes something must have gone wrong. So because something must have gone wrong, it uses the ARQ part. What does ARQ here mean? Automatic repeat request. Because we timed out, okay, we did not get an acknowledgement. It realizes that something must have gone wrong. So let me just repeat sending the same thing. Automatically repeat the request that I'm sending. Or in other words, simply repeat sending frame 1. So what it does now, it sends frame 1 now. Look at this. During this whole process, my variable at R is still 1 because it is waiting for frame 1, right? Its variable will not change here. Its variable continues to be 1 itself. So now once it sends frame 1, this time let's say the frame 1 reached successfully. If the frame 1 reaches successfully, then the receiver will send ACK0 and change its variable to R equals to 0. Once it receives this, then again S becomes 0. Now it will send frame 0. Right? So on and so forth. Okay. So this is very, very important. The concept of a timer and timeout. Timer and timeout. This is very, very important in stop and wait, because if the sender doesn't receive the acknowledgement within the timeout period, timeout is often written as TO, right? If in most mathematical calculations, we write timeout as TO. If it doesn't receive it, it will wait for that time. And once the time outs, it will set some timer. It will set some timer for itself, right? A reasonable amount of time, right? Once it doesn't get it, it will simply resend the packet. Very simple scheme here. But of course, the total time now to send frame 1 has increased because we waited for these 5 seconds. We did not get any response. Then, see, look at the total time here. We started sending the packet here. Look at this. We started sending the packet here. And when we started sending the packet, we switched on the timer. So this whole TO got wasted plus TT plus 2TP, because we have seen TT plus 2TP earlier, right? For a perfectly transmitted package, including acknowledgement, this is the time it takes. So TT plus 2TP if there is no error. But since we have error, we have to add TO to that. Okay, that's very important. Cool. Now, so this is what happens if you have a lost frame or a lost data frame. This is one case. The other case is lost acknowledgement frame. Any frame could be lost, right? So what happens if you have an acknowledgement frame that is lost? Okay, let's look at that case. Again, whenever we are designing any protocol, we have to think of all these cases. It's very, very important. So I have my medium now. So let's assume I sent frame 0, I got acknowledgement 1, I sent frame 1. So when I'm sending frame 1, my variable here is S equals to 1 and the variable here is R equals to 1, right? So the receiver receives frame 1. Cool. The receiver receives frame 1 and he sends acknowledgement 0. Now what is he going to wait for? The receiver is going to wait for frame 0 now. Remember, because he has already sent the acknowledgement, he'll change his variable to 0 and he's now, whatever the variable here is, that's the frame that he or she is waiting for, right? So now this is waiting for frame 0, right? Not frame 1. It sent the acknowledgement. It sent ACK 0, but this acknowledgement got lost somewhere in the medium. Now what happens? Now how does it look from the sender's perspective? The sender doesn't know whether the frame did not go or the acknowledgement did not come. As soon as the sender sends the frame, it starts a timer. Look at this. It starts a timer. As soon as it sends this frame, whenever it sends a frame, it starts a timer. Okay, it waits for TO time, the timeout time, and that doesn't get an acknowledgement. And remember, the receiver also does not know. Remember, in these instances, neither the sender nor the receiver knows that something is going wrong in the medium, right? They don't control the medium. Things can go wrong in the medium. They can only send data, place data on the medium. They don't know if something goes wrong in the medium itself, right? So what the sender does is, okay, the sender waits for timeout time. It doesn't get the acknowledgement. So what does it do? As it knows, it doesn't know whether frame 1 got misplaced somewhere or acknowledgement got misplaced. It doesn't know. It doesn't know whether it's a case of lost frame or lost acknowledgement. It doesn't know that. So it will simply automatic repeat request. It will simply resend frame 1. But remember, when it sends frame 1, my receiver is waiting for frame 0 because it thinks I've already sent you an acknowledgement. right? But now this sends frame 1. So what does it do? It simply discards. It simply discards. It simply discards. Okay. And it says, why is it discarding? Because it already got frame 1 here. And it's waiting for frame 0, but it was sent frame 1 again. So it realizes that something is wrong and it will discard. It will discard, but it will send an acknowledgement. This is very important. Discard, but it sends an acknowledgement saying, I am looking for frame 0, not for frame 1. So it sends ACK0. If this ACK0 successfully reaches here, look at this. If this ACK0 during this whole period, remember during this whole period, my variable S will be equal to 1. If this ACK0 successfully reaches here, then I know, okay, now I should send, see, ACK0 basically means I've received frame 1 successfully and please send frame 0. So it changes its variable to S equals to 0 and sends frame 0. This is how it works. Okay, this is called the lost acknowledgement frame case. Very interesting case.